All right, so welcome to Unit 8. This unit's called stoichiometry, which is like a big weird word. It just really means measuring elements. It's Latin for measuring elements. When you hear the word stoichiometry, a lot of students often think chemistry math. So that kind of scares people. What I want to kind of refer to it more as is that it tells us the amount of stuff that we can make with a reaction. That's stoichiometry. All right, so let's get down to a real definition for stoichiometry. It uses a reaction's balanced equation, which gives us how many, to determine the masses, or how much, of products are actually formed. The balanced equation, so to kind of shorten that up, the balanced equation equals moles, and that equals how many. So let's look at a real simple chemical equation here. Just take water, and let's go through the electrolysis process. So we break it apart into its constituent elements. We've got two diatomic molecules, hydrogen and oxygen. Probably should go ahead and balance that. And if we were going to take a look at how many things are produced, that would be the moles. So for every 2 moles of water we react, we're going to get 2 moles of hydrogen and 1 mole of oxygen. That's how many. But that doesn't tell us how much. How much, and I know it sounds like a small difference, but how much refers to the actual masses of that stuff. That would be like how much or what mass of hydrogen could we produce or what mass of oxygen could we produce. Because even though moles are really, really helpful, we do not have a mole scale inside of the laboratory. All of our scales measure in grams. So if I want to be able to measure or to be able to produce 18 grams of a particular substance, let's say oxygen, I would need to know exactly how much mass of water I needed in order to do that. So the balanced equation equals moles, that equals how many. It's the stoichiometry then that equals mass. And that tells us how much. Well, if you know how many moles you're going to make, 1 mole of oxygen, you can use stoichiometry to figure out exactly the mass of oxygen that you'll produce. And one of the biggest keys when you're working with the stoichiometry, when you're changing from mass to moles, is to always keep in mind that we have this wonderful tool from the periodic table known as the molar mass. And it's the molar mass that's really going to help us with this conversion between how many and how much. All right. Here's a little visual that's kind of neat. We have 2 reactants, a red reactant and a green reactant. We got a lot more red than we got green. A reaction is run. We get 2 products. We get a blue product and a purple product. And because there was a lot more red stuff, we've got a little bit of red stuff left over. The really big question of this unit is going to be, well, how much of this do we have left over? And how much of this do we form? And how much of that do we form? That's going to be our end goal or our end game for this chapter. So let's look at the approach we're going to use to figure out the stoichiometry thing. We're going to use what's called a BCA table. So it's called the BCA approach. The BCA approach to stoichiometry emphasizes the balanced equation. It uses the balanced equation to really figure out this stoichiometry. The first step in working with stoichiometry, trying to figure out how much or how many moles are going to be produced, is to balance the equation. So that's no different than we've seen in the past. So here's my first example. You don't have to write down all the words, the hydrogen sulfide gas, which smells like rotten eggs. You don't have to write that down. But this stuff, it burns in air, so it's combined with oxygen, and when that occurs, it produces SO2, sulfur dioxide, and water. And a good chemist would look at that equation and say, okay, we need to balance it. So we got these coefficients, 2, 3, 2, 2. So let's put that into what we call our BCA table. So the chemical equation always heads the BCA table. It comes first. On the left side, then, we're going to put the 2 words before and change. We want to think, okay, before the reaction occurs, how many things do we have? Okay, how many things do we have? Well, we're only given one number in the entire problem, and that's this one right here. The problem tells us a little bit about the hydrogen sulfide. It tells us that we start with 2.4 moles. When we're all said and done, we're going to have an after then too, and we'll get to that in a second. All right. So we got to fill in the before line. That's step number 1. Now remember I said we've got 2.4 moles of the hydrogen sulfide. So that is what we start with. That's before the reaction occurs. And you might say, well, we know nothing about oxygen. And in fact, we do. If you're burning something in air, you probably have an abundance of oxygen. Like you've got the entire Earth's supply of oxygen to use in order to burn this stuff. Like wildfires burn for weeks on end, and they don't extinguish because of a lack of oxygen. So we have plenty of oxygen. So I'm going to write the 2 letters XS. They stand for XS. Oh, you guys get it. Okay. All right, so but before the reaction, we have no products. So on the right side of my yield zero with the sulfur dioxide and the water, I put 0 and 0. Now remember, I'm referring to moles here. I'm asking the question, how many? So I've got 2.4 moles of H2S. I've got an excess number of moles of oxygen. I have 0 moles of SO2. I have 0 moles of H2O. Now, how does this change work? That's the next question that we'll ask. Now, the change has got to focus on the molar relationships. Okay? Assume that more than enough oxygen is going to react. We've done that already. And here's a little image that's going to kind of show you that. I've got like a ton of reds. It doesn't matter how many reds you got. If you only got 1 blue, your reaction is going to be really limited by that blue molecule. Okay? That's the idea of my oxygen and hydrogen sulfide thing. Okay. All right, so step 3. We're going to use the ratio, very important to understand this term right here, the word ratio. We're going to use the ratio of coefficients to determine the change in the amount of stuff that we start with. All right, so let's put up our table again. You can just add this to your existing table. Now, if the reaction occurs and it flies away, if we start with 2.4 moles of hydrogen sulfide and we have a ton of excess oxygen, when the reaction runs to completion, it runs to its end, we're going to have something that runs out first. Well, if we have a total excess of oxygen, that thing that's going to run out first is the hydrogen sulfide gas. So we say that we are going to lose 2.4 moles. And that lose is the negative sign. You see the little negative sign right there? Yeah, that's the lose. Okay? On the other side of the yield zero, I'm going to skip to the other side of the yield zero real quick. You'll notice that the coefficients for hydrogen sulfide, sulfur dioxide, and water are all the same. That means that if I lose 2.4 moles of hydrogen sulfide, I will gain that many moles of SO2, and I'll gain the same number of moles of H2O. You might say, well, how can that be? If I lose 2.4, I can only gain 2.4 on the other side. But remember, there's a rearrangement of the atoms to make new molecules. But even still, there wouldn't be enough atoms in order to make all the stuff on the right side. Well, primarily because we've got some oxygen here, and we don't have any oxygen there. Well, that oxygen comes from our second reactant. So how do we know that there's a 3.6, a negative or a minus 3.6 underneath the O2? Well, it comes from the ratio of the coefficients. So, to the right of your BCA table, you're going to have a section that's called the work section. You can just write the word work, or you don't have to do that. Just understand that you want to put all your work to the right. That's fine. Got to be something that I can see. So you start with the total number of moles. Well, Cornick, let's see. I had 2.4 moles of H2S. When you do this, don't forget unit and label. Now let's think about what we did. We want to compare that to the amount of oxygen needed for the reaction. Okay? So I want to get rid of the H2S. So I'm going to use the coefficients in my next ratio here. This is the molar ratio in order to switch from H2S to O2. When I fill in my little unit analysis table here on the right side in red, I should notice that my moles of H2S actually cancel out. One on top, one on the bottom. And what am I left with? I'm left with moles of O2. Exactly what I was looking for. Because it's moles of O2, that will go in right there. So on your calculator, this is pretty simple. It's just 2.4 times 3 divided by 2. Hey, you should even be able to do that in your head. And you're going to get 3.6. Now wait a minute, Cornick. It's not 3.6, it's negative 3.6. Yes. And that's because reactants are always consumed, so they get a minus sign, and products always accumulate, so they get a plus sign. So now we can complete our table. We now have found out that we are going to lose all the hydrogen sulfide. We'll still have a tremendous excess of oxygen because there's a lot of oxygen. And then if we ask the question, how many moles of products are formed? Well, we have that answer, 2.4 moles of each. It is important to understand that change in the final state are not equivalent to each other. Okay? Just because in this particular example, that number and that number are the same does not mean that they equal each other. There will be times where this number and this number will not be the same. Okay, so you need to understand that you're not always just taking that number and putting it down there. Because you'll see, and sometimes we actually start with some of this stuff. Instead of it being 0, it's a different number. So then you'll have to take this number plus this number, and you'll get that number. All right, so like I said, we always want to complete the calculations on the side. So I did that little mole ratio in red on 2 slides ago on the right side. And we will get to this last portion tomorrow. We don't want to do mole to mass conversions today. We're going to just stay with the moles. Okay? So all calculations stay to the side. And we'll pick up right here tomorrow. All right, a little bit longer than I thought it would be, but not too bad. We'll see you in class tomorrow. We start off tomorrow with some cookies. It's a good day.